Hi everyone. In this video we're going to discuss what's called the law of large numbers that goes with section 7c. The law of large numbers is a way to calculate an average that uses probability. So basically what they do is they repeat a process or an experiment over and over and over again through many trials, and they come up with this number. It's a different way of calculating an average than the mean is. The mean is when you add up all your values and divide by however many you have. This type of average takes into account probabilities of different events happening and gives you an average in the same kind of way. But sometimes events are more heavily weighted than others, and this is going to give you an average that takes into account if that is the case. This is an example of a computer simulation that actually ran. This is real data. This is not just a made up picture here, where the computer simulated flipping a coin over and over and over again. It did 100 trials of it, and then it kept track of how many heads it came up with. You can see towards the beginning of the graph, it doesn't necessarily come up 50-50, but as the coin is flipped over and over again, it tends to go down into this middle area, which is 0.5. You would think that it would happen about 50% of the time, and that's what actually does happen. To calculate expected value, you have to first decide how many different events you have. So it's helpful to look at everything and just lay out all of your possible outcomes ahead of time. Then you assign each event a value, you multiply by the probability of that event happening, and you add up each separate piece until you get to the end. This will probably make more sense when we look at the examples, so let's take a look. This is an example of a theoretical expected value because we're going to roll a die. The question wants to know the expected value for the outcome of a roll of a fair die. So first thing we got to do is figure out what could happen if we roll a die. All the possibilities for rolling a die is 1, 2, 3, 4, 5, and 6. Those are all of our events. So I'm going to take each one of them and multiply that value by the probability of that happening. So if I roll 1, 1 becomes the event, and I have a 1 out of 6 probability of rolling a 1. Plus, the next outcome that could happen, or the next event, would be a 2. There's a 1 out of 6 chance of rolling a 2. Or I could roll a 3. I have a 1 out of 6 probability of rolling a 3, plus 4 times 1, 6, plus 5 times 1, 6, times 6 times 1, 6. All of the possible outcomes have been accounted for, and their corresponding probabilities are multiplied. Next, which you can plug this all into your calculator at once, by the way, but I multiplied each set of parentheses together. So 1 times 1 over 6, 2 times 1 over 6, 3 times 1 over 6, and so on. And since you're adding all of these pieces up, I just kept them as 6 so I'd have a common denominator, and I added up the top. I got 21 over 6, which I then divided to get 3.5. So the expected value for the outcome of rolling a fair die is about 3.5. What does that really mean? What it means is if you were to roll a die over and over and over again, let's say you roll it 1,000,000 times, and you kept track of how much you were getting. So let's say the first time I roll a 1, then I roll a 4, then I roll a 6, then I roll another 1, then I roll a 2. If I kept track of all of that and found the mean in a different way, averaged it out, what it says is based on probabilities, it would be about 3.5. If you look at the original set of all the outcomes, 3.5 is right in the middle, which is exactly where you would expect this average to be. If you were to calculate the actual mean for this by adding up 1 plus 2 plus 3 plus 4 plus 5 plus 6 and dividing by 6, you would also get 3.5. So it's a different way of finding an average, and it accounts for probabilities. This one happens to be the same, this expected value and this average is the same as the mean because we're talking about a theoretical amount. Here is another illustration of several computer simulations now that were done of rolling a die. So basically what you're looking at is four different dice that were rolled, a red one, a green one, a blue one, and a purple one. And the computer kept track of what came up. So on the red, it looks like they got a 3, then they rolled it again, got a 1, and so on and so forth. After you repeat the experiment over and over and over again, the average starts to come to the actual mean, which is 3.5. Okay, but in real life, the probabilities are not usually all equal. In real life, usually probabilities are varied. So here's an example of how you would use expected value to calculate something from a business standpoint. The question says, based on data from past claims, an automobile insurance company has determined the probability for auto claim amounts for drivers ages 16 through 21 to be as follows. And then they give you this table here. About 70% of these drivers don't file any claims, meaning they don't get into any accidents, and they don't cost the company any money. About 15% of them file small claims of $2,000. About 8% file claims of $4,000. 5% is $6,000, and then 1% is 8, when the extra 1% is $10,000 or more. So large claims for that. The question then says, using this data, what is the expected value of a claim payment for a given year for these people aged 16 through 21? So what we're going to do to calculate this is the amount of the claim will be the event value, and we're going to multiply each one of those by their corresponding probabilities. The easiest way to do this is to just extend the chart out and make another column. So 0 times the probability, $2,000 times its probability, $4,000 times its probability, and so on. When I multiplied this out, I got these values here. And now, since these are all of the values in parentheses, I'm going to add up all of this together and get one expected value. So the expected value for a claim payment for these age drivers would be about $1,100. What this means for the company is they should charge at the minimum $1,100 for a premium for each of these people. $1,100 is their break-even point. That will give them enough to cover the bad drivers, the ones who file these large claims. And it also is why, even if you don't file any claims, that's why insurance companies still collect your premium, because they need money in the pool to cover these other people who are filing those large claims. If they charge anything less than this, eventually there won't be enough money left in the pool to cover the larger claims. The good drivers pay for the bad drivers, in other words. Anything above this, based on probability then, would be profit for the company. So if the company was looking to make a $50 profit per person, then they should charge $1,150. $50 would become profit for each policy sold then. Here's another example of insurance and how insurance works, but this one is going to account for a premium up front. So it's going to be a little bit different when we set up the chart. It says, suppose an automobile insurance company sells an insurance policy with an annual premium of $200. Based on data from past claims, the company has calculated the following probabilities. An average of 1 in 10 policyholders will file a claim of $500. 1 in 20 will file a claim of $1,000. 1 in 50 will file a claim of $2,000. And they want to know what is the expected value to the company for each policy sold. So always keep in mind when you're setting up all of this data what perspective you're looking at this through. We're going to look at this through the company's perspective, not the actual individual person who is buying the insurance. Okay, so here is how we're going to set this table up now. We're going to use each of the claim values as the outcomes. Now, when I set this up, I like to put a description first, which then helps me assign an accurate value. So from the company's perspective, one thing that could happen is that the individuals file a $500 claim. But from the company's perspective, if they do that, then the company has to pay out $500. So they're going to lose $500 from having to pay out this claim. However, they're going to collect $200 from the individual from their premium, which means that they can apply that to their claim, and the company then only has to come up with $300. They'll have to pay that out, so it's negative for them, but that's what the company will actually have to pay. It said that 1 in 10 file that much, so I put that in fraction form and then converted it to a decimal because they're easier to work with usually. Next is the $1,000 claim. So from the company perspective, they would have to pay out $1,000, which makes it a negative value for the company. They'll apply the person's premium to it that they collected, which means that they would only have to come up with $800 to pay out this claim. The information said that 1 in 20 people file that, so I did the same thing, put it in fraction form and divided, and got a decimal value. The third thing that they listed was a $2,000 claim, so I did the exact same thing. From the company's perspective, they would be out $2,000. They'll apply the premium, which means that they'll have to pay out $1,800. 1 in 50 people file that much, which is about 0.02 or 2%. What they don't tell you now is that there is also an option for no claim. If there is no claim, the company still collects the $200 premium. They don't have to pay anything. They just keep that $200 for each policyholder. And the reason I knew that this had to exist is because my probabilities so far didn't add up to 100% or 1. What I did was then used the probability of something not happening. So if I add this up, 0.1, 0.05, and then 0.02, I get 0.17, not 1. So I have only accounted for 17% of the policyholders so far. That means that 83% or 0.83 have not been accounted for. So I worked this backwards, in other words. I figured out how much I had so far and then subtracted it from 1 for it not happening, for not having a claim. Next, I have to figure out the actual expected value. So now that I have my outcome values and I have each probability, I multiplied each of those together and got these values: -30, -40, -36, and 166. The negatives do make a huge difference because then when you add it up, your expected value will be $60 for this insurance company. That means that they should expect to make about $60 in profit for each of these policies sold. They are charging a $200 premium, but then applying some of that to the pool, and they get to keep the $60. The next example talks about bidding on a design for an architect. So an architect is considering bidding for the design of a new museum. The cost of drawing plans and submitting a model is $12,000. The probability of being awarded the bid is 0.2, with anticipated profits of $60,000. What is the expected value in this situation? So again, I created a table to figure out what's going on here. My outcomes are we either win the bid or we don't, we lose. If we win, we can expect to make a $60,000 profit. However, after submitting the plans and all of the fees, we'll be out the $12,000, which means we'll only net $48,000. The probability was given as 0.2. If we lose, that means we still had to submit the plans. So we still had to lay out the $12,000. We'd be out that much then. So we would be negative. And to find the probability of this, I did the same thing as before. I subtracted it from 1 because the probabilities need to add up to 1 or 100%. Then I multiplied each together, 48,000 times 0.2 and negative 12,000 times 0.8, which gave me an expected value of 0 when I added it up. What this means is, based on probabilities, you could expect to make no money because your probability is low that you'll actually win this bid. You have a lot to gain if you do, but the probability is low that you'll actually win. Probability is high that you'll actually lose. So you don't really have anything to gain here. If your expected value came out negative in this situation, you should not bid at all because based on probability, you would be out money. If it comes out positive, then you have a really good chance of winning, and it's probably a bid that you might want to take a chance on. So this is 50-50. You could go either way. The next example says, in a product liability case, a company can settle out of court for a loss of $350,000 or go to trial losing $800,000 if found guilty and nothing if found not guilty. Lawyers for the company estimate the probability of a not guilty verdict to be 0.75. What is the expected value of the amount the company could lose by taking the case to court? If the company takes it to court, then we only need to worry about the guilty or not guilty verdict. If it takes it to court, that means it's not going to settle out of court. So this value is not used for the expected value. So what could happen? We're either found guilty or not guilty. If we're guilty, we're out $800,000. If we're found not guilty, nothing happens. And the probability was given to us as 0.75, which means the other one must be 0.25, so that this adds up to 1. Next, I multiplied that together, the value times the probability plus the other value times its probability, and I got an expected value of negative $200,000. So what it's telling you is, based on probability, this is what you could expect to lose. This amount, negative $200,000, is a lot less than what it would be if we settled out of court. In other words, you should not settle. You should take the case to court and roll the die because you have a very high probability here, 75% chance of being found not guilty. The next one says a roulette wheel has 38 numbers, 18 black and 18 red, and the numbers 0 and 00 are green. You pay $1 to bet on a single number, and if the ball lands on that number, you're awarded $36. If the ball lands on any other number, your dollar bet's collected and you win nothing. Find the expected value for playing roulette if you bet $1 on number 20. So the two outcomes are we either win or we lose. If we win, we collect $36, but it costs us $1 to play, so we only make $35 off of that. If we lose, we win nothing, but we are still out our $1, so it's a negative $1 for that value. To figure out the probabilities now, I set this up in fraction form. Because there's only one number 20 on the roulette wheel and there's 38 numbers altogether. That means that 37 of them out of 38 are not number 20 because these have to add up to 1 or 100%. Also, I'm going to leave them in fraction form for as long as possible because if I change them to decimal form, they're irrational. And if I round them off too soon, as I'm going through the calculation, my final answer might be too far off. So I'm going to work with them in fraction form for the calculation and round my answer at the end. So I multiplied each value times its probability and added each piece. I got 35 times 1 over 38 plus -1 times 37 over 38 is negative 37 over 38. Since these have common denominators, I just added the top. 35 plus negative 37 is -2 over 38. And at the end is when I divided to change it to decimal form. This comes out to be about negative 0.05, which is about 5 cents. What it means is if you played this game over and over and over again, you could expect to lose about 5 cents per game on average. And with that, that's the end of this section. You should now have what you need to be able to complete the homework for section 7C.